Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you've ever looked at a perfectly designed piece of equipment, say a massive industrial heat exchanger, and thought, that looks simple? Well, today's deep dive is here to maybe shatter that illusion a little. We are not just looking at the theory of how heat should flow, We are fighting the engineer's eternal battle against real-world imperfection.
That's absolutely right, yeah. We're moving from the pristine world of theoretical thermodynamics to the messy reality where things break down, surfaces get gunked up, measurements lie. Our mission today is really to unpack the sources that detail how engineers quantify and control these factors. We're talking things like thermal decay, managing critical measurement errors, synthesizing mountains of imperfect experimental data into a reliable predictive model.
Right.
Because in the field, performance isn't just about picking the right material. It's often dominated by factors like, well, geometry and just plain mechanical degradation over time.
Okay, so let's start with the ideal scenario first. We base pretty much everything in thermal analysis on the resistance analogy, treating heat flow like current in an electrical circuit. We define the general thermal resistance, R, as the temperature drop, delta T, divided by the heat flow, Q. It's elegant, really.
It is. And for simple one-dimensional conduction, it's beautifully defined. R equals L divided by the product of K times A. That's length L over conductivity K times area A. That is the perfect foundation for, say, a simple slab of material. Nice and clean.
But almost immediately, we start intentionally complicating things, right? Usually to boost performance. The easiest way to increase heat flow is to dramatically increase that surface area A, usually by adding fins.
Fins are a wonderful tool, absolutely. But they introduce the first major, let's say, betrayal of the ideal model. Heat has to travel along that fin, and as it does, the temperature gradient drops. This means the fin out at its tip isn't transferring heat nearly as efficiently as the base.
Okay.
And this forces us to introduce the concept of overall surface efficiency, eta sub OV.
So it's not enough just to maximize the surface area. We have to account for how effective that area actually is.
Precisely, yeah. Our sources show the outside surface efficiency, eta sub of comma O, is calculated by looking at the fraction of the surface that is finned, S sub FO, relative to the total surface area, S sub O, and then multiplying that relationship by the fin efficiency itself, eta sub FO. The core insight here is that a fin must be optimized for size, material, and geometry. A gigantic fin made of the wrong material, or one that's just too long, can actually be a net negative because its efficiency just plummets.
So you're just hauling around dead weight at that point.
Exactly. Dead weight that isn't doing its job properly.
Okay, now let's talk about what feels like the true enemy of long-term design, fouling. This is where those beautiful lab results go to die, isn't it?
Oh, absolutely. Fouling is catastrophic, really, because it's the inevitable real-world accumulation of insulating substances, scale, grime, sludge, that constantly degrades the system's performance over its life. Engineers must design the component to survive years of operation, meaning they have to factor in a potentially massive performance penalty right from day one.
How significant are we talking here? Is it a minor tweak or?
Oh, it's enormous. Often. We are essentially adding an insulating layer whose resistance is often far greater than the actual film resistance of the fluid itself. I mean, look at some of the data points from the sources. Process liquid streams, like, say, caustic solutions, they show fouling resistances around 3.5 times 10 to the power of negative 4 square meters Kelvin per watt.
Okay.
But if you're dealing with something like heavy fuel oil, that resistance can jump way up, maybe to 12.3 times 10 to the power of negative 4 square meters Kelvin per watt. That's a huge design challenge, almost an order of magnitude in some cases.
Wow. And when you have these geometry changes like fins or this dynamic degradation like fouling, the heat transfer coefficient is definitely not uniform across the entire surface anymore. So how do we calculate the performance of the whole heat exchanger then? You can't just use the simple log mean temperature difference, can you?
No, you really can't. Not reliably. We have to employ tools that handle that non-uniformity. And this is where the effectiveness NTU method, or epsilon nu2 method, comes in.
Right, the epsilon.
Yeah. It's a necessary analytical tool that calculates performance based on how close the heat exchanger gets to its maximum theoretical performance, which is crucial when film coefficients or fouling are varying significantly because of the geometry or the process conditions changing. It gives us a reliable way to design these things even when the conditions are complex and, frankly, messy.
Okay, so we've established that physical reality is imperfect. The margins we build in for things like fouling and fin losses are only as good as the measurement we take to begin with. But trusting the thermometer, or whatever sensor we're using, that's its own engineering challenge, right?
It absolutely is. Measurement at its core is a relative effort. It's all about comparison against some agreed-upon standard. Our anchor point for temperature, for example, is the International Temperature Scale of 1990, or ITS 90. It's defined by fixed points, like the triple equilibrium state of water at precisely 273.16 Kelvin. Everything else relates back to that fundamental point.
But the very sensor we use to compare the temperature can betray us. I'm thinking specifically about hysteresis in thermocouples. That sounds like a nightmare.
It is. It's the ultimate measurement artifact, really. Hysteresis means the sensor output depends not just on the temperature now, but on its immediate history, where it's just been.
Okay.
So for a thermocouple, you might find one sensitivity curve, let's say 1.5 millivolts per degree Celsius, when the temperature is rising. Pretty straightforward. But when the temperature begins to fall, the sensitivity changes, and often non-linearly. It might follow a completely different complex function like ST equals 1.5 times, open parenthesis 2.33 minus 0.133T plus 0.0033 squared, close parenthesis, millivolts per degree Celsius.
Wait, hang on. So you're saying we have to calculate if the device is heating up or cooling down just to trust the number coming off the sensor?
Uh-huh. To be truly precise, yes.
Wow. That sounds like overkill until you realize that calibration error could completely sink the whole process analysis.
Exactly right. Precision demands that level of detail sometimes. So once we gather a collection of these complex, carefully calibrated measurements, we then have to quantify our confidence in them using statistics. We define the deviation, d sub I, of any single measurement, t sub I, from the average, t bar. Pretty standard, and we use the standard deviation, sigma, to quantify the precision and the spread of all our measured values.
Okay, makes sense. But what happens when we get a measurement that just looks wrong? You know, a wild outlier that throws off the whole data set. We can't just toss it out because we feel like it, can we?
No, you definitely need mathematical justification for that, and that's where Chauvinet's criterion comes into play. This is kind of the mathematical defense you give your boss when you throw out that one data point that would have ruined the entire project budget or conclusion.
Okay.
The criterion is based on a probability rule.
Mm-hmm.
Essentially, the probability of obtaining a certain deviation by chance should not be smaller than 1 divided by tuck-in, where n is your total number of measurements.
Can you give us a concrete example of that? Like, what's the barrier?
Sure. Let's say you perform 10 measurements, so n equals 10. The criterion dictates that the maximum acceptable deviation from the mean is 1.96 times the standard deviation, sigma. So if a data point falls outside that 1.96 sigma boundary, you have the statistical authority, based on this criterion, to reject it as a questionable outlier. It protects the integrity of your experiment.
Got it. So it's a justifiable way to clean the data. Okay, so we have clean, statistically validated data points. But often the final result we care about, let's call it Q, depends on inputs from multiple sensors, say T1, T2, and T3. How do we track how the tiny uncertainties from each of those inputs combine and affect the final answer?
Right, this is the problem of uncertainty propagation, and the Klein and McClintock method provides the rigorous framework for handling it. Conceptually, the idea is to make sure that your overall uncertainty in the result, U sub Q, is calculated by rigorously combining the individual measurement uncertainties, U sub I. You calculate this using a square root of the summation of terms, where each term basically accounts for how sensitive the final result Q is to a small change in that specific measurement. T sub I, scaled by the uncertainty U sub I of that measurement itself, all squared.
Okay, so it sounds complex mathematically, but the goal is to avoid underestimating the total error.
Exactly. It prevents engineers from being overly confident and drastically underestimating the error bars on their final calculated answer. Super important.
That makes sense. So once we trust the combined uncertainty, we usually need to convert that reliable data set into something usable, like a predictive tool, an equation, or a curve fit.
Precisely. If you measure, say, a fluid temperature T versus the heating power, Q dot, you typically use the least squares method to find the line or curve that best represents that relationship. It works by finding the coefficients for your proposed function, maybe a straight line, maybe a polynomial, by minimizing D, which is the cumulative sum of the squares of the distances between your measured points and the fitted line.
Right. So it doesn't let one wacky point skew the whole line too much.
Exactly. And crucially, when calculating the standard error of that curve fit, epsilon, you have to use n minus p in the denominator. N is the number of data points, and p is the number of coefficients you determine for your fit. This properly accounts for the degrees of freedom you used up in finding that best fit line.
And this whole rigorous process, careful measurement, statistical validation, uncertainty propagation, and then curve fitting, this is how we get those predictive rules that really underpin practical heat transfer design, right?
Yes, absolutely. This is how experimental measurements are synthesized into generalized, often dimensionless, convective correlations. We eventually arrive at equations like the one for the Nusselt number, nu, which equals some constant c times the Reynolds number, Rh raised to the power of n times the Prandtl number, Pr raised to the power of m. This relationship, derived from countless experiments fitted this way, tells us how heat transfer scales with fluid speed, that's the Rh part, and fluid properties, the Pr part, in a predictable, experimentally verified way. It's powerful.
But how do we validate the model itself? We've verified the individual data points using Chauvinet's, maybe, but how do we prove that the distribution of our experimental data actually aligns with the theoretical model or curve we created? Is the fit actually meaningful?
Good point. That's where the chi-square test comes in. It's a really foundational statistical test. It essentially compares the expected distribution of data points based on your theoretical model or curve fit against the observed distribution, what you actually got in your real-world experiment. It helps engineers confirm whether the model they built is truly representative of the underlying physical phenomena, or if maybe they're just drawing a line through random noise that doesn't really follow the pattern they think it does. It validates the goodness of fit.
Okay, that makes sense. It's like a final check on the whole modeling process. Let's apply some of this precision thinking now to what feels like the modern battlefield of thermal engineering, electronic cooling. When we're trying to cool tiny, powerful chips, we face resistance at interfaces. And you mentioned there are sort of two main types, macroscopic and microscopic.
Correct. The macroscopic resistance is the one most people think of first. Thermal contact resistance, or subco. This is caused by surface asperities, basically, the microscopic roughness and imperfect physical contact when you press two surfaces together. Even seemingly smooth surfaces only touch at a few points.
Right, and that's what we use thermal interface materials for, to fill those gaps.
Exactly. Then there's the microscopic resistance, which is maybe less intuitive. The thermal boundary resistance, R(B). This occurs even at a nearly perfect atomically flat interface.
Okay, explain R(B). Why does that exist if the surfaces are almost touching perfectly? What's resisting the heat flow then?
It's down to physics at the atomic level, really. Heat in solids is primarily carried by packets of vibrational energy called phonons. Think of them like sound waves, but at much higher frequencies. R(B) exists because the phonons in chip material A literally don't speak the same vibrational language as the phonons in material B, the heat sink material, for instance.
Right.
There's an acoustic mismatch. Those thermal vibrations don't efficiently pass across the boundary because the materials have different vibrational properties. This creates resistance. It's usually only significant at the actual transistor level or maybe at very low temperatures, but it illustrates the incredible depth of the complexity we deal with.
Fascinating. Okay, so back to the macroscopic R subco.
Yeah.
To combat that, we use thermal interface materials, or TIMs. Often these are particle-laden polymers designed specifically to fill the air gaps. But I remember reading that using the TIM material with the absolute highest bulk thermal conductivity can actually backfire. Is that right?
That's one of the greatest counterintuitive trade-offs in thermal design. It really is. TIMs are often filled with highly conductive particles like boron nitride or diamond dust to increase their bulk thermal conductivity, kappa sub TIM. Makes sense, right?
Yes, seems obvious. More conductive filler, better heat transfer.
But adding more of these hard particles also increases the mechanical rigidity, or the shear modulus, of the polymer matrix material itself. And increased rigidity means the material resists being deformed. So it leads to a thicker bond line, delta, when you assemble the parts. It also means a smaller real contact area, a subreal, because the stiff material can't conform as well to the microscopic surface roughness.
So the material becomes too stiff to properly squish into all those tiny surface crevices and make good contact.
Exactly. It resists being squeezed into that ultra-thin layer you ideally want. Because of this conflict, better bulk conductivity versus worse mechanical conformance, the minimum overall thermal resistance, which means the best thermal performance, might actually occur at particle loadings that are less than the maximum possible concentration.
Wow.
Yeah, you can literally over-engineer the material's bulk properties and end up hurting the critical mechanical contact needed for the thermal path. It's a balancing act.
Okay, that is counterintuitive. Speaking of high performance, we have to touch briefly on heat pipes. These things seem almost like magic in their efficiency sometimes.
They are phenomenal devices, yeah. They operate using phase change liquid evaporating in one section, vapor traveling, and then condensing in another section, all driven by capillary forces within a wick structure. Their effective axial thermal conductivity is truly astonishing. A simple heat pipe using water can reach effective conductivities around, say, 100,000 watts per meter per Kelvin along its
Oh,
length.
100,000.
Yeah. Compare that to solid copper, which is one of our best conductors. At only around 400 watts per meter per Kelvin, it's orders of magnitude difference. Just incredible devices.
And finally, let's look at a really cutting-edge technique.
Yeah.
Immersion cooling. Using these special low boiling point dielectric fluids, highly efficient, potentially, but it introduces this massive stability issue called incipience overshoot. What's going on there?
Right. Incipience overshoot is a serious headache. It's basically an unwanted thermal shock caused by delayed boiling. These dielectric fluids, like FC72 for example, have a surprisingly high solubility for air. They literally dissolve the air out of the tiny microscopic cavities that naturally exist on the chip's surface.
Okay, why does that matter?
Because those air-filled cavities are normally the nucleation sites, the easy starting points for boiling to begin. When they're gone, filled with liquid instead of air, it takes a much higher surface temperature, a higher superheat, to initiate boiling. So the surface gets hotter and hotter, then boiling finally does initiate, but it happens almost violently and suddenly over a large area. This causes an undesirable spike in temperature followed by a sudden, jarring drop as the vigorous boiling quickly cools the surface.
So that initial spike followed by the rapid crash, is this the overshoot?
That's the overshoot. And that thermal cycling, that shock, is a major design challenge for long-term component reliability. You don't want your chip going through those rapid temperature swings repeatedly.
Definitely not. Okay, so to sort of tie all these complexities together, maybe we end where engineers often start their transient analysis with a critical simplification tool, the Biot number.
Yes, the Biot number, BO. It's fundamental because it essentially gives you permission to simplify reality sometimes. It's the ratio of the internal conduction resistance within a solid body to the external convection resistance at its surface. Mathematically, Bi equals H times L divided by K, where H is the convection coefficient, L is a characteristic length, and K is the thermal conductivity of the solid.
And the magic number is 0.1.
Pretty much. If the Biot number is less than about 0.1, it means the internal conduction resistance is negligible compared to the resistance to heat getting away from the surface. This implies that the temperature inside the body is essentially uniform at any given time. And if that's true, we can use the much simpler lumped capacity solution for transient analysis, treating the whole object as being at a single temperature that changes over time.
So it's the metric that saves you from a potential lifetime of solving unnecessarily complex partial differential equations for internal temperature gradients.
You got it. It tells you when you can ignore those internal details and still get an accurate answer for the overall cooling or heating behavior. It's a hugely important simplification tool.
So we've really traveled quite a path today, from the ideal foundation of thermal resistance through the sort of statistical rigor needed to trust even a single data point into the messy, material-driven world of fouling and the sometimes counterintuitive design of things like TIMs. We've seen that modern engineering isn't just about applying a perfect equation from a textbook. It's really about wielding this whole toolbox, things like the Biot number, the epsilon-2 method for exchangers, statistical validation like the chi-square test to manage, model, and ultimately survive real-world imperfection.
And what's really fascinating when you step back is realizing that pretty much every engineered component is a complex collection of compromises, isn't it? I mean, just think about something like a printed circuit board. Considering the incredibly complex interaction between the thermal vias trying to pull heat out, the anisotropic conductivity of the board materials themselves, all those different trace layers for electricity. How many layers upon layers of interconnected thermal and electrical compromises are embedded just in the structure of the devices you use every single day? And maybe more importantly, how many distinct analytical checks, experimental validations, and statistical tests, like the ones we discussed, were required just to ensure those devices function reliably without melting. It's quite staggering when you think about it.
Until the next equation, design junkies, we are mechanical engineering made simple.